So this is the first notebook that I wrote to help you get started in Colab. The first code block is to make your Google Drive accessible. And then I also set up this base directory. This is similar to the code block that Jeremy put in his first notebook. Okay, the next thing that you have to do once you've done this, you want to update Fast.ai according to the instructions that Jeremy the Fast.ai administrators provided. And so there's just one line of code to run here. I might just run this as we go so you can see. Okay, so because it's pretty quick. Oh yeah, now I have to do this. Oh, never mind. I think I won't run it in real time because I have to go and, oh well, I'll do it. Okay, open the next link, get the authorization code. So what this does is it sets up a link that you click on, then you have to sign into your own Google account, and then you have to give permission for Google to for the Google account to look at your Colab account. Then you have to copy this link, which I'm going to do now. Then go back to the notebook, and then oops, wrong notebook. Where am I? Go back to the notebook. Oops, that isn't what I wanted to do. Go back to the notebook. There it is. Okay, now I'm going to paste in the authorization code that I just got, and then go. And now, all right. So while one person is waiting, I'm going to admit that person. Now we have 22. Okay, so that ran. So now I'm in. Then you update. Okay, then I'm going to actually do this step, updating Fast.ai. It should be pretty quick. Done. All right, and the next thing, and this is the step that trips up a lot of people because the Fire is, I don't understand everything about Fire, but it's a library that you need to be able to run command lines from a notebook. And Jeremy does that all the time. And so let's do that. Let's install Fire and then also NB convert. I'm not sure if we're going to need this or if it's already installed, so I'm just going to install it anyway. All right, so that's done. All right, the next step is we're going to go to the course, the course v3 repo, the repo we're going to have to clone it from Git in our drive because we need to have access to all the notebooks and all the scripts that Jeremy and that Sylvain wrote, so that we can, because you need access to those scripts. That's why a lot of times if you try this from Colab, it won't be successful because you don't have the notebooks accessible. So we're going to do that. First, we're going to create a directory for the courses that we're going to clone into. And in my case, the directory already exists, so it didn't do anything. Then we're going to clone the repo into that directory. And in my case, I've already done that, so it tells me that the directory already exists. This is not an empty directory. So, but in your case, if you run this for the first time, it's going to actually clone the repo to your drive, so where you can get at it. All right, and now you want to go to the folder in the repo that has the course, that has this course in it. So you change directory and list it, and there you can see all the notebooks. All the notebooks are there, as well as this exp directory that we're going to use. And let me see, and these .py files, which are the scripts that we're going to have to use. So now we do have everything accessible to us in our on our Google Drive.
Just one question. Why don't we update the our repository of the course notebooks? So looking at the code, we only git clone, or maybe we should do like git pull or something, because I believe they can keep updating those things.
Yes. Yeah, so once you've done this the first time, then you can probably change that to git pull so that it just updates. Yeah,
okay.
Good point.
Yeah.
That's a good point. But in fact, it installs pretty fast, so you know, that may not be an issue. Okay, then the next thing you want to do is to save this notebook, the one that we're working from. This is just a code cell to remind you to do that. How to do it? You pull the file menu here. I'm going to do it here. Hit file and then hit save, and then it saves it. Okay, and now you have this notebook. Now you'll have this notebook to use in the future. Okay, and next we want to test it. So we're going to run the very first notebook. And it did it. So let's see, from notebook. Oh, you know, I think I made a mistake here. I didn't actually run the first notebook. I just got ready to run the first notebook. So the next thing I can do is I can actually get the first notebook and run it. And then from here on, for each successive course notebook in the repo, you open it with Collaboratory, and then you modify it by inserting this code cell at the top, and before you run it, and then you run it. This code cell basically sets up your drive environment and makes it available for you to work from. Okay, let me see if so this is an error here. I didn't actually run this first notebook, but let me see if I can do it. If I open a notebook from, let's see, from my drive, there it is. I'm going to open the first notebook. So you see what I did? Let me just go back, and what I did was I hit File, Open. Let's see, open a notebook right there. Okay, so this is something I should modify. I will modify this notebook to add these instructions. This is how you open the first notebook or any other succeeding notebook. So you hit File, then Open Notebook, and then you have this menu from Collaboratory, and you can go to Google Drive, because that's where your notebooks are now, and that's this notebook. This is the first notebook in the class, so I'm going to open that. And there you see it. Zero, zero. This is the wrong name. Sorry, this looks like the same notebook we've been working from, but that's not what I want. Save this notebook containing. Hold on for a sec. Oh, I think I see. I opened the wrong notebook. This is something I've been playing with before. I'm going to do this again. Open notebook, go to Google Drive, and then the one I want is 00 exports. 00 exports. I have a lot of crap in here, and it's hard to find. Let's see.
You went in the top.
Yeah, it's got. This is the one I played with. This isn't the exact right one, so I'm going to search 00 underscore exports. See, there's a double underscore after it, so I changed the name. That's the one I want. 00 exports. Copy of. Hopefully this is a pristine. I think I must have overwritten it or something, because I don't see it. But let me see if one of these copies is the right one. Let's see. I want the pristine file that just the way it came. Let's see, take out of trash. No, that's I guess I had trashed that one. Let me try something else. Recent. There it is. Okay. Okay, now I had already done, so the instruction that I gave was to copy that cell at the top of the notebook, and that's what I did here. So you have to do this. You have to insert a cell and then copy that text block, the last text block in that initialization notebook, right? So you copy that cell there. Then we execute it to make the Google Drive accessible. And it wants an authorization code again, so I'll do that. I'll just open this link. Go in there, log into my Google account, allow Google to access everything, and then here's the code. Go back to the notebook. Okay, copy the authorization code and execute that. Oh, 2 people waiting, admit them. Okay, not now. Okay, that's done. Okay, so now we're going to we're going to run the first notebook to prove that this really works. Okay, so this is the first cell, execute it. The second cell, the third cell, the fourth cell, and let's see. Okay, so this one here writes. It uses. This is where you use fire. I've already executed it and it worked. So, oh nope, it didn't work. It said it doesn't have access to fire. Okay, I found a problem. I thought I just executed fire. I thought I just sort of installed fire. So, okay, so there's apparently a problem with this because it's not able to access the environment that I already set up for it.
Yeah, it looks like you have to do it in every notebook.
Yeah, that's kind of inconvenient. I shouldn't have to do that.
No.
I'm going to leave this at this. I'm going to come back. I'll think about this afterwards and figure out what went wrong. But meanwhile, try it out and see if it works on your machine, because I have a feeling I might have done something wrong, gotten the notebook from the wrong place or something like that. Anyway, so I'm going to continue, but I'll try to fix this notebook for next time. Okay, so I'm going to go now to the first notebook, which is y square root of 5.
Joseph, there's a question on the chat about the setup notebook. Is it on your Google Drive, or can you share the link?
I did share it. You should be able to get it. Yeah, you should be able to get it from this Slack group. The Slack group associate the what is it? DL. Let me see. Fast.ai _DL, that channel, the one that we have for this meeting. I pinned it, so you should be able to find it. It's also on, let me see, I'll just share it right now on chat. Copy the link, go to the chat. Can I get to chat? Let's see. Oops. Oh, God. Okay. I'm having trouble finding the chat from the Zoom menu. How do I get to the chat? Can somebody let me know?
If you get your mouse pointer to the bottom, you should have the menu with the invite participants, share. There's the chat as well.
I see manage participants. I see. Do I have to get out of sharing to do this then, or?
Maybe, I don't know. No, I don't think so.
Okay.
In this case, might be at the top. Maybe on your screen it's at the top.
All right. Let's see. Chat. There it is. Okay. All right. So here's the link. Paste it in there. And there. Can everybody see that?
Thank you.
Okay, I'm going to try that link to make sure it worked. And yeah. So basically, I'm linking to the forum where I put this link. So now if I click on that link, can everybody see this screen where I'm in the forum now?
Yes.
Okay, I'm going to click on Jupyter Notebook. This is the link that I sent you from chat. I'm going to hit this thing, and it's going to load another copy of the notebook. That's the notebook that we're running in. Okay. Okay. So there, everybody can get to that notebook now. All right, back to y squared root of 5. And apparently Jeremy and company found an error, and Jeremy found an error in the initialization, in the timing initialization routine in PyTorch. And this goes through and talks about it. I'm not sure I got the point, but let's run the notebook and see what happens. All right, so I'm going to run the notebook. So you see, here's what you're using. He's using Fire to do this. And this is that x.nvo2 import. See, this is the thing that he saved from notebook 2, this file. And now we're bringing it into our environment here so that we can access it. So we'll do this. Now, and also what we're doing, the second thing we're doing is we're getting this data set, the MNIST data set again, and we're normalizing. He's defined a function here that normalizes it, subtracting the mean, dividing by this standard deviation. Then he looks in, I'm not sure why he executes this here, but we're basically having a look inside of this conv.nd, the torch.nn.modules.convolutions, conv.nd reset parameters. So the two question marks say, let's look inside this function and see what it does. So there it is, reset parameters. It's going to do timing uniform initialization of the weights. And it's this A parameter is, if you remember what a leaky ReLU is, does everybody remember that? It's where a ReLU is when you take in the negative half line, everything is set to 0, and in the positive half line, everything is set to itself. It basically filters out all the negative values. That's what the ReLU does. A leaky ReLU, instead of setting everything in the negative on the negative branch of the x-axis to 0, it sets it. It gives you a multiplier, which we call A. So instead of 0, it gives a multiplier, and sometimes the multiplier that they use is small, like 0.01, so that it's close to being a ReLU. It's close to 0. But in this case, they're not using 1. They're using a rather large multiplier here, because they're using square root of. Let's see, the multiplier A is square root of 5. So that's a pretty big multiplier. So this is a leaky ReLU. And then this is the timing uniform initialization of the weights. And then the next step is to initialize the biases, if there are biases. So if the bias is not none, then you initialize the bias between these two bounds, square root of fan in. In this case, fan in, I think it's going to be 1. There's one input in, which is just the x, the data set. All right, so that's what that does. But now we're going to go back. We're going to load and normalize the MNIST data. That's what this cell does. We get the training set and the validation set. And now we can, I'm not sure what this view does, but let's try it. It gives me the size.
Reshaping the function.
I think view reshapes as like NumPy reshape, rearrange.
Oh, okay.
Yeah.
Okay, great. Let me make note. Thank you. View reshapes. An array. Okay, so it's reshaping the array according to the prescription here. So I think the initial input is 28 squared. They flattened out the images, I think. Let's verify that. And then, so then the view is reshaping it, like Michael said, it's reshaping those images into 28 by 28 images. But let me just go back and run this again, and then we can verify. Insert cell below, and then I can do x valid dot shape and see what we got. Yeah, 784. So the input is, in this case, we're looking at the validation. There are 10,000 examples, and each one of them is an array of length 784, which happens to be 28 squared. So what he's doing, thanks to Michael, we see what he's doing here. He's taking the training data, reshaping it to basically recreating the images out of this array, right? It's reshaping the 784 pixels into a 28 by 28 array. Fine, so that's what we've done. Let me execute that again. And then here he's defining a number of channels, number of filters for the convolution layer. So n is just going to be 10,000. We saw that, or 50,000, because here's the, oh sorry, it's the training shape. So n should be 50,000, and c is y train max. What's y train? Y train is the label, that is the digit that this image is supposed to represent. Remember, it's the MNIST data, and each of these 28 by 28 images is supposed to be of a digit between 0 and 9. So y train dot max is 9, right? The maximum digit you can have is 9, and then he adds 1 to it, because so now we have c, which tells us the number of possible outputs, basically 0 through 9. That's the number of possible outputs, the length of that. So we have 10. C is going to be 10. The number of NH is the number of channels for the convolution that we're going to use. So he's basically setting that up. And then we can see that, again, N is 50,000, like we said, because it's the size, the length of the training data. And C is just a scalar. Well, it's just a tensor with a value of 10, right? So now we're going to define this convolution layer, 32 channels with a 5 by 5 kernel. That's what this is doing for us. Okay, and now he defines a subset of the validation set so that we don't have this unwieldy data set. We'll take just the first 100 elements of the validation set, and then we can see its shape, 100, and then it has the 28 by 20. So there's 100 elements, and each has a 28 by 28 image in it. Next he defines this function called stats, which just gets the mean and standard deviation. Oh, there's one person waiting. I'm going to admit them. Okay. All right. So now let's look at the shape of the weights of this. Remember, L1 is this convolution that we defined. The shape of the weights is what we expect. 32 channels with a 5 by 5 convolution in each channel, right? And we can actually look at these weights. And there's 32 of them, 32 of these 32 of the channels. So each one of these little blocks is a channel with a 5 by 5 convolution in it. And there it is. Okay, move on to the next cell. Now we're going to apply this stats function that we defined just to get the mean and standard deviation of the weights and the biases. And we can see that the mean is 0, close to 0. The standard deviation is 0.1. Which is not really what we want, but that's what we're going to do. We're going to end up trying to make it closer to, make the standard deviation closer to 1. So let's see, we're going to now apply our linear layer to the input, which is the reduced validation set, and then look at what we got. So the output is expected. We have 100 elements in the output. There are 32 channels, and 24 by 24. This part I'm not sure about, why the output should be 24 by 24. So I'm going to have to think about that a little bit, and I will. but not now. Okay. And just make myself a note.
Isn't that because of the convolution and no padding being done? So 28 by 28, you lose 2 pixels on either side.
Oh, okay. So this is an artifact of the convolution layer that we applied, right?
Because we haven't added any padding.
Okay. I'm going to make a note.
Or it could be otherwise related to the stride.
Yeah, stride. Yeah. So we have to figure out why this is so. Why 24 by 24? Michael suggests it has something to do with padding and stride. So we can follow that up.
We can look at the Excel sheet which Jeremy had shared. So in that, when we take convolutions of it, like 3 into 3 layer, it condenses that to a single value. So for the edges, usually we won't get anything unless we take padding.
Okay, that's right. Okay, so this is we can probably figure this out why it's 24 by 24. Because it's related to the padding and stride. We have to have some padding in order to be able to make this work. So anyway, that's the shape of our output, and now we can get the statistics on it. And now we see that the mean is still close to 0, but the standard deviation is now closer to 1. So that is because of this initialization that we did, I believe, or not. Let's see. Nope, I guess we didn't do the initialization yet. So I'll have to understand. So we see the standard deviation is not 1 yet. So the next thing we're going to do is we're going to apply the timing initialization to the weights. And this is underscore normal. So that means he's going to initialize it from a normal distribution rather than a Gaussian distribution. And in this case, A equals 1. And this is sort of a clever trick to make it a linear layer. This means that you're not using the ReLU. You're basically allowing negative values. That's what A equals 1 is. It's the slope of the negative branch is 1. Okay? So this is equivalent to just a regular linear layer, and we're initializing it this way. And then we'll look at the standard deviation and mean. And so it did work the way we wanted. The mean is 0, the standard deviation is close to 1. Okay, then he imports this this functional thing from NN, from torch.nn, and it allows us to define a standard ReLU by using this method in this functional as it's called leaky ReLU, and its inputs are the linear layer, the convolution layer that we defined, and the slope for the ReLU, for the leaky ReLU. And in this case, if we wanted a standard ReLU, we would make A equal to 0, and that's what he does in the next. So that's why this is a so now we're actually going to do this. Let's see. This is just, we're going to actually do this. Well, we didn't make L1. Hold on. I'm not, okay. So this is just the definition. We haven't really run this function yet. So, there it is, stats F1. So we're now going to initialize, run the statistics on it, and we find that it successfully gave us something with a standard deviation close to 1, which is what we're looking for, but the mean is now away from 0. So, okay. And let's see, now we're going to, let's see, what is this L1? It's the same one, it's the same convolution, but I'm not sure. I'm not sure this is the ReLU followed by the convolution. This is defining L1 all over again. I think we already did this step. Yeah, there it is right there. So we're just defining this layer again. I'm not sure what this is right. It's just the linear layer again. All right. So we're going to run this. We're going to look at its size. We're going to look at the first channel of that is the 5 by 5 convolution filter, and then he defines this thing called receptive field size, which is basically this 5 times 5, the number of elements in this thing. So it's 25. Receptive field size is 25. He looks at the shape of the weights, L1.weight.shape. So 32, NF and NI are the first two elements in the shape. So there's NF is the number of filters, and F is for filters or channels, I guess. And then, so there's 32 channels. That's all he's doing. And then he defines these things called fan in, fan out. Fan in is the number of, is basically the NI, which is 1 times the receptive filter size, which is 20, which is the size of the size of the convolution filter, which is 5 times 5, 25. And then fan out is NF, which is 32 times 25, and that's 800. So then he defines this gain thing, and I've made myself a note. I don't understand why the formula is this, but he's using it. So I just noticed that for a linear layer, A is 1. So remember, so the gain, so if you run this formula, you'll find it's just going to be 2 over 2. It's going to be, the gain is going to be 1. For a ReLU, A is 0, and so the gain is just going to be square root of 2 over 1, which is the square root of 2. And when A equals square root of 5, which is what he did here, remember, he defined the leaky ReLU with the negative slope, the slope of the negative side being square root of 5. So in this case, the gain is 0.577, which happens to be 1 over square root of 3, by the way, because you can evaluate this formula as square root of 2 over 1 plus 5. That's the square root of 2 over 6, which is the square root of 1/3. So that's where that number comes from. All right. So then we just look at these numbers again that we just went through. Let's see. Define zeros. Let's see. Torch.zeros.uniform. So this is the uniform initialization, the standard deviation of the uniform initialization performed by PyTorch, and we see that it's 0.577. So he sort of reverse engineered to find out, well, I mean, no, this is the reason why is because it's got that square root of 5 in the definition of it. So that's why this comes out that way. And again, we remind ourselves that square root of 5, that number comes from 1 over square root of 3. That's where this 0.5766 comes from. And ultimately, it comes from this formula with which apparently Jeremy is reverse engineering, and he thinks this is the formula that they're using. Anyway, so now here's the chiming. Now Jeremy writes his own chiming initialization, and then he shows that it gets you the same result. I'm not going to spend too much time on this. And then, yeah, I'm just going to leave this now because I think he's basically tried to reverse engineer what they've done and shown that he can write his own chiming initialization routine that does the same thing as the one in PyTorch. All right, next thing I'm going to do, and I don't think I've left myself enough time for this, but hopefully you guys can go through this. This is, I'm going to overwhelm you with let's see. Let me make sure that I got this. Yeah, I'm going to overwhelm you with some math here, but I think it's a good thing. And because Jeremy's goal is for us to be able to read papers, and this is going to help you to deal with some of the math you're going to see in papers. All right, so I'm just going to do this, get to the point where I want to be. Okay, he has shown what happens if you if you continually multiply randomly initialized matrices by each other. So here X is like a dummy stream of input data, a column of 512 values, and A is the dummy weights matrix, which is and he defines that as a 512 by 512 matrix. And then he just continually multiplies A by X to get, and remember, when you take A by X, you're going to get a column vector of dimension 512. So you can just continually do this. You can continue to multiply A by X, and then X equals A by X, and then continue to, in other words, you're multiplying again and again by this matrix. And then you end up with NANDs. It blows up. The activations will blow up. And you can even find out when it happens. So we'll do this again, but now we'll stop when it blows up, when it first becomes a NAND, and find out what index that was. And it was 28. So on the 28th iteration, you already have blown up. Things have already blown up. So and then he says, okay, what happens if you initialize with too small of a matrix, a random matrix, and then if you run this loop again, then eventually you just get zeros. So you either get an exploding activation or a vanishing activations, and this is a problem. So that's why you need initialization. And then he goes through this initialization thing. Again, we start with a 512 column vector and a 512 by 512 weight vector, but he divides it by square root of 512. That's the trick. And then we run this loop again, and this time it ran all the way through and it didn't blow up. Okay, even we could run it 1,000 times and it'll still it did kind of blow up there, didn't it? Let me try that again. He ran it 100 times and it worked. Now I'm going to try it 1,000 times to see if it still works. Nope, it kind of blew up. It didn't get to be a NAND though, at least. So anyway, 100 times. You can run this 100 times and it still stays within, oops, I have to initialize it again, sorry.
Is 100 like 100 layers?
100, this is a loop of 100 iterations. So notice what you're doing. You're replacing X by the product of A times X, by the matrix.
So does it kind of like represent 100 layers in a network? So maybe 1,000 like too much?
Yes, that's exactly right. Yeah, that's like applying a layer on top of a layer on top of a layer. So it sort of mimics building a deep neural network, right, with 100 layers. And previously, a few years ago, they would have a lot of trouble if they tried to build deep layers. But now with this new initialization technique, you can build layers that are as deep as 100. And there it is. So you take the, let me start again, initialize again, run this loop again, look at the output again. And again, see the mean is 0 and the standard deviation is not 1, but not too far from 1. So it works. Okay. Magic number, he says the magic number, it calls it square root of 1 over 512, and it's 0.04. So that's what we're multiplying this, that's what we've multiplied this by, 1 over square root of 512. So in other words, instead of initializing with this random matrix, we initialize by this sort of normalized or normalized random matrix. And so initialize again, X. So yeah, initialize again, take the mean and standard deviation. And just to show that this is indeed initialized with a normal standard normal distribution. Oh, there's a person waiting. I'm really sorry about people that didn't get in because they're waiting and I didn't notice. All right, so the next thing he does is he runs this cell where he, again, does this loop. And X, he initializes X, which is a column vector of 512, and A, which is like sort of like a weights matrix of 512 by 512. And then he computes the matrix product, Y equals A matrix times X. Then he starts accumulating the mean. So he's adding, he's taking the mean of this result, that is this mean of this 512 column vector, taking the mean, and item basically extracts the float from a tensor. So he's so you can deal with numbers here. So mean, you're just adding this, you're adding this 100 times, right? Because you're doing the loop of 100. And you do the same thing with this SQR. Now you're accumulating the sum of the y squareds. So that is the mean of the y squared, sorry. So you have this y, this column vector of 512 length. We square it, right, which just means squaring each element. So that still gives us a column vector of 512. And then we take the mean of that column vector, and then we extract the floating point number out of it, and we add it to, we're accumulating the sum. So then at the end, we divide by 100, because we know that we've added together 100 of these things, so we want to figure out what's the average one, right? So what do you get? You run this, and you get 0.06 and 501. And he says that he points out that the standard deviation looks very close to the dimension of our matrix. When you compute y, you sum 512 products of one element A by one element of X. The mean and standard deviation is 1, and so you're just adding together 500 values, 512 in this case, really, values of 1. Why is it 500 and not 512? Well, because we only average together 100. If we average together 1,000, we'll get a closer, we'll get the number closer. All right, so then he does this. I'm not sure what he's doing here. That's right, he's doing it 10,000 times now. But let's see, what did he do differently? And 1. Oh, in this case, we just did 1. Instead of 512 elements, we just did 1 element. And it basically shows that, yeah, we have a Gaussian normal distribution with mean 0 and standard deviation close to 1. Next he does, now this is the thing that I'm focusing on, and I'm at the end of the lesson, and I wanted to spend most of the lesson on this, but we'll see. So now he runs this, and he runs this, it's 1,000 times. We're basically going to multiply x times a, and the dimension is going to be 1. We're going to do the simplest possible thing. We're just going to multiply a random number x times a random number a, and sum up the mean and the square, and then take the average. And so this time we did that, and we get this number 0.314 and 0.481. And I've altered this notebook, and I'll share it later on so that you can go through it if you want to. The main part that I've altered is I've added this this screen full of math here, and I wanted to go through it. But what struck me when I saw this was, why is this number 0.314 and why is this number 0.481? And it turns out that, well, we can go through the math and figure it out. For people that didn't want to go through the math, basically we show in this math section that the output of a linear layer followed by a ReLU has a mean of 1 over pi. That's what this number is. It's 1 over pi. Oh, and remember, sorry, this thing here makes it into a ReLU. We're basically applying that if y is less than 0, we set it to 0, and otherwise we keep it. Okay, so this is basically the ReLU. I should put a little note in there. So he's giving this elementary demonstration of what happens when you try to initialize and initialize with a random distribution, and then what happens after you apply the ReLU. And so I go through all this math to show that the expected answer is that the mean should be 1 over pi, and the SQR should be 0.5 if the when the inputs are initialized by sampling from a unit normal Gaussian, which we've done. And this agrees with the empirical results from the previous cell. 1 over pi is that 0.314, and the 0.48 is supposed to be 1/2, and indeed would get closer to 1/2 if you made more iterations, right? And so all of this is the math that it takes to demonstrate that. And I would like you to read through it if you have the time, because it explains everything in really great detail, and it assumes nothing of you except that you know what a Gaussian, what a normal distribution is, a zero mean unit variance normal distribution. So let me see if I can go through this in a few minutes. Probably it'll be hurrying, but let's try. So we start with A and X, which are independent Gaussian random variables. That means that means they're drawn from a normal distribution with zero mean and unit variance. And then Y is defined to be the product. Okay. Now the effect of the Rayleigh layer, when you apply the Rayleigh to Y, what you're doing is you're drawing Y from a mixture distribution. Half the time the input X is going to be less than 0, so Y is clamped to 0, i.e. replaced by 0. And the other half the time, X, the input, is greater than 0, so you're just going to draw Y from a positive half Gaussian. And then I have this link to a half Gaussian. It's basically, you know what a Gaussian is? It looks like a bell-shaped curve. A half Gaussian, a positive half Gaussian, is if you chop off the negative side of that bell-shaped curve and set it all equal to 0. That's a half Gaussian. So now what we're doing in the empirical, in this little cell here, what Jeremy's doing is he's basically calculating the expectation value of Y. That's what this mean is. And square, SQR, is the expectation value of Y squared. So that's what we would like to calculate. So what I'm really doing here is I'm trying to analytically, so this is empirically finding the expectation value of Y and the expectation value of Y squared. That's what this little cell does. It finds it empirically. What I want to do is I want to understand analytically why we got these numbers out, and that's what I'm doing here. All right, so to start with, so let me repeat this. So for the mixture distribution is half the time we draw X from the negative real values, and half the time we draw X from the positive real values. And the mixture distribution is basically saying that that the distribution is with probability of a half, Y is 0, and with a probability of half, Y is drawn from this half Gaussian. All right. So the next thing we do is we calculate the expectation value of Y. And according to the mixture distribution, we have the mean is really the expectation of Y. That's the definition of mean, of what we mean. This thing defined as mean is really the expectation value of Y. This is mathematical notation for the expectation value, which is basically an average. Okay, so E with square brackets of Y means expectation value of Y. Applying the mixture distribution, we're going to have 0.5 times the expectation of 0, right? That's the negative half, plus 0.5 times the expectation of A times X, because that's Y on the positive side. Okay, so that's 0. The expectation value of 0, the expectation value of a constant is itself, so 0.5 times 0 plus 0.5 times the expectation value of A times X. Now, the expectation value of a product of A times X is just going to be the product of the expectation values, because A and X are independent. So we end up with 0.5 times expectation value of X squared. So that means that to calculate the mean, all we got to do is figure out how to calculate expectation value of X under the half Gaussian distribution. All right, so if we go to the wiki page that I linked to there, you'll see that the probability density function for the half Gaussian, that is what you're plotting when you're plotting this bell-shaped curve, is 1 over sigma, sigma being the standard deviation of the Gaussian, which in our case is going to be 1 because it's unit variance. And then square root of 2 over pi times e to the minus x squared over 2 sigma squared. That's the formula for Gaussian. And by normalized, I mean that the integral of this half Gaussian from 0 to infinity should be 1. And that's why you get this funny normalization factor in order to make the integral equal to 1. So then the expectation value of x, what is the definition? Sorry, is there a question?
Yeah, we have 2 minutes past 7, so I'm not sure.
Sorry, I think. I'll just quit here. If you want to, you can read this. It's just as good as me explaining it to you because I've written it out as carefully as I can. And you can send me any questions you have about this, and I'll be glad to answer them. And then the rest of this notebook I didn't really modify. So I'm going to stop there.